Imagine discovering that your entire life has been observed through a one-way mirror and you're just now noticing the glass. For 70 years, we've wondered why the universe seems empty despite containing billions of potentially habitable worlds. We call this the Fermi Paradox, the great silence that surrounds our planet. But what if the silence was never empty? What if it was careful? Right now, something called 3I-ATLAS is racing through our solar system with chemistry that shouldn't exist, timing that seems too convenient, and behavior that's making scientists whisper uncomfortable questions. Stay until the end to discover why this cosmic visitor might prove we're being studied by intelligences who prefer to watch from the shadows. Part 1. The Silence of the Stars. Picture this. 400 billion stars, 400 billion suns, each potentially warming worlds of their own. In our galaxy alone, we're talking about planetary systems numbering in the trillions. Rocky worlds, gas giants, moons with subsurface oceans. The mathematics of possibility stretches beyond comprehension. And yet, nothing. No signal, no message, no hello, echoing across the cosmic dark. This is the Fermi Paradox, named after physicist Enrico Fermi, who posed a deceptively simple question during a 1950 lunch conversation. Where is everybody? It's a question that should keep you awake at night, though tonight we'll let it gently carry you towards sleep instead. Consider the arithmetic for a moment. Our galaxy formed roughly 13 billion years ago. Earth took 4.5 billion years to develop complex life, and just a few million more to produce a species capable of sending radio waves into space. If similar processes occurred elsewhere, even on just a tiny fraction of those trillions of worlds, we should be swimming in alien chatter by now. But we're not. The silence is so profound that scientists have proposed only 3 reasonable explanations. First, intelligent life might be extraordinarily rare. Perhaps we're the cosmic lottery winners, the one in a trillion accident that somehow stumbled into consciousness and technology. It's a lonely thought, but statistically possible. Second, maybe civilizations tend to vanish. They reach a certain level of development and then something happens. Nuclear war, climate collapse, artificial intelligence gone wrong. Some universal stumbling block that claims every species right before they learn to reach for the stars. Scientists call this the Great Filter, a cosmic sieve that catches civilizations just as they're getting interesting. Or third, and this is where things get intriguing, they're out there but they're keeping quiet. Maybe there's a galactic ethics code, a universal prime directive that forbids interference with developing worlds. The zoo hypothesis suggests we're living in a carefully maintained preserve, observed but not contacted. Or perhaps the universe operates under darker rules, where broadcasting your location is tantamount to painting a target on your world. Speak up, and something hungry might come calling. But here's what most people don't realize. The game has changed. We're not just listening anymore. Every night, automated telescopes sweep the sky, digital sentinels scanning for anything unusual, anything out of place. The Asteroid Terrestrial Impact Last Alert System, ATLAS, operates 4 telescopes across the globe, photographing the entire visible sky every 48 hours. They're looking for asteroids, of course, rocks that might threaten our world, but sometimes they find something else entirely. Sometimes they find visitors from the space between the stars. In recorded history, we've confirmed only 3 objects from beyond our solar system. 3 wanderers that originated somewhere else entirely, travelled for millions or billions of years through the interstellar void, and happened to pass close enough for us to notice. The first was discovered in 2017, the second in 2019, the third arrived this year. And unlike its predecessors, this one is behaving in ways that make scientists whisper among themselves in conference hallways. Ways that might, just might, offer a clue to the great silence that surrounds us. Tonight, we're going to follow this cosmic visitor on its journey through our solar system. We'll examine the evidence with the careful eye of science, but we'll also dare to ask the questions that linger at the edges of respectable research. Could this wanderer from the dark be natural? Almost certainly. Could it be something more? Well, that's what makes for interesting conversations. We'll explore the mystery in 3 acts. First, the arrival and discovery of our enigmatic visitor. Then, a survey of the cosmic puzzle that is the Fermi Paradox itself. And finally, we'll consider what it might mean for science, for humanity, for our place in the universe, if this wanderer carries secrets from the stars. So, settle back. Let your mind drift outward, past the moon, past the planets, to the space between solar systems where ancient travellers make their slow way toward distant suns. The universe is about to tell us a story. Whether it's a story of ice and rock and natural physics, or something altogether more extraordinary, remains to be seen. But either way, the silence of the stars has been broken by the arrival of something wonderful and strange. Part 2. The visitor called 3I-ATLAS. Every few years, if we're lucky, the universe delivers a gift from the cosmic deep, not wrapped in ribbons but cloaked in ice and dust, travelling faster than anything gravitationally bound to our sun should ever move. On July 1st, 2025, one of those gifts arrived. Its name is as bureaucratic as government paperwork: 3I-ATLAS, formerly designated C, divided by 2025 N1. The 3I means it's the third confirmed interstellar object we've ever seen. ATLAS credits the survey telescope that first spotted it, scanning the southern sky from Chile with the patient persistence of a digital bloodhound. The formal designation follows astronomical convention, the year, the half-month of discovery, and a sequence number that marks it as the first such object found in that particular 2-week window. But names matter less than what this thing represents: a messenger from somewhere else entirely. The discovery came during routine observations, the kind of methodical sky patrol that happens every clear night around the world. ATLAS, with its 4 wide-field telescopes, photographs the entire visible sky every 2 days, comparing each image against previous ones, looking for anything that moves. Most of the time, they find asteroids, chunks of rock orbiting our sun in predictable patterns. Sometimes they find comets, dirty snowballs following elliptical paths that carry them from the outer reaches of our solar system to the inner warmth, then back again. But on that July night, something different appeared in the data. An object moving too fast, in the wrong direction, on a trajectory that broke all the rules. You see, everything in our solar system is gravitationally bound to the Sunday asteroids, and comets might swing out to incredible distances, but they're still prisoners of our star's gravity well. Their orbits are ellipses, closed curves that bring them back again and again, sometimes over millions of years, but always eventually returning home. This thing was different. Its path through space was hyperbolic, an open curve that would carry it through our solar system exactly once, never to return. It was moving roughly 19 kilometers per second relative to our sun, fast enough to escape our gravitational embrace entirely. That speed, that trajectory, could only mean one thing: it came from interstellar space, and it's heading back there. Think of it as a cosmic highway traveller, briefly exiting at our solar system for fuel and snacks before merging back onto the interstellar interstate. Except this traveller has been on the road for millions, possibly billions, of years. The mathematics of its journey are staggering. Based on its current trajectory, we can backtrack its path through the galaxy. This wanderer likely originated from the direction of the constellation Lynx, though pinpointing its exact stellar neighbourhood is impossible after so much time and distance. It may have been ejected from its birth system by gravitational interactions with giant planets, or perhaps its parent star went through death throes that sent chunks of itself spinning into the void. Either way, it's been travelling through the space between stars longer than complex life has. Existed on Earth. As October approaches, 3I-ATLAS is heading toward its closest approach to our Sun, what astronomers call perihelion. On October 29th or 30th, depending on precise timing calculations, it will reach its minimum distance of about 1.4 astronomical units from our star. That's roughly 210 million kilometres, comfortably outside Earth's orbit, but close enough to feel the sun's warmth and begin the ancient dance of ice turning to gas. For Earth, the encounter is even more distant. Our visitor will pass no closer than 1.8 astronomical units from our world, about 270 million kilometres, or roughly 170 million miles. That's nearly twice the distance between Earth and the Sunday. No cause for alarm, no reason to cancel weekend plans. This is astronomy, not Armageddon. But here's what makes 3I-ATLAS special. Unlike its famous predecessor, Oumuamua, which remained frustratingly inert and asteroid-like throughout its visit, this newcomer is putting on a show. It's developed what astronomers call a coma, a cloud of gas and dust surrounding its nucleus, along with the beginnings of a tail. Classic comet behavior, the kind of activity that happens when ancient ices warm in the sun's radiation and begin to sublimate directly from solid to gas. The ATLAS survey, which discovered our visitor, represents a revolution in how we watch the sky. 4 telescopes, in Hawaii, South Africa, Chile, and another in Hawaii, work together as a global network, each equipped with cameras capable of imaging enormous sections of sky in a single exposure. They're not looking for beauty, they're looking for change. Anything that moves, anything that brightens, anything that appears where nothing was before gets flagged for follow-up observation. It's this kind of systematic robotic vigilance that has changed our odds of catching interstellar visitors. Before automated surveys, we might have missed 3I-ATLAS entirely, or noticed it too late to gather meaningful data. Now, we can track these cosmic wanderers from the moment they become bright enough to detect until they fade back into the interstellar darkness. But as our instruments have grown more sophisticated, so have the mysteries they reveal. Because while 3I-ATLAS might look like a comet, it's beginning to behave in ways that make astronomers reach for their calculators with unusually furrowed brows. The universe, it seems, still has surprises to share. Part 3. A Growing Mystery. When the Hubble Space Telescope turned its sharp eye toward 3I-ATLAS in early autumn, the images it sent back were both beautiful and puzzling. Our interstellar visitor appeared as a teardrop-shaped cocoon of dust, glowing faintly in reflected sunlight. The physics seemed straightforward enough. Solar radiation was pushing tiny particles away from the nucleus, creating the classic comet tail that always points away from the sun. Regardless of the object's direction of travel, it was textbook comet behavior, except the textbook was written for objects born in our own solar system. The first hint that something unusual was happening came from size estimates. Measuring the actual nucleus of a comet, the dirty snowball at its heart, is notoriously difficult when it's surrounded by a bright, expanding cloud of gas and dust. It's like trying to estimate the size of a light bulb when you're staring directly into its glare. Current calculations suggest the solid core of 3I-ATLAS spans somewhere between 320 meters and 5.6 kilometers across. That's a range wide enough to drive several space shuttles through, sideways. The uncertainty exists because the growing coma increasingly hides the nucleus from view, like fog obscuring a distant building. What we can see is the cloud. What we're trying to measure is the source. But it was the James Webb Space Telescope that revealed the first truly strange detail. JWST, with its infrared vision, can peer through dust clouds and analyze the chemical composition of the gases streaming away from the nucleus. What it found was unexpected: an unusually high ratio of carbon dioxide to water vapor, about 8 parts CO, 2 to every 1 part H, 2O. Now, you might think, so what? It's a different mix of ingredients. But in the world of cometary science, ratios like this are nearly unprecedented. Most comets we've studied, including the previous interstellar visitor 2, I divided by Borisov, show much more water relative to carbon dioxide. Water ice is common throughout the outer reaches of planetary systems, where temperatures drop low enough for H2O to freeze solid. Carbon dioxide, however, freezes at even lower temperatures. To end up with such a CO2-rich composition, 3I-ATLAS would have had to form in an extremely cold environment, or perhaps suffered some kind of intensive radiation exposure that preferentially removed its water ice over millions of years of interstellar travel. The plot thickened in late August when ground-based telescopes began detecting hydrogen cyanide, HCN, in the comet's growing atmosphere. Now, before you start worrying about cosmic poison clouds, remember that we're talking about incredibly tiny amounts of gas spread across millions of cubic kilometers of space. The detection required sophisticated spectroscopy to identify the characteristic signature of cyanide molecules fluorescing in sunlight. What made this interesting wasn't the presence of cyanide. Many comets produce HCN as they warm up, but the timing. The gas appeared gradually, strengthening over several weeks as the comet drew closer to the sunday. It suggested that different types of ice were sublimating at different temperatures, like layers of an onion peeling away as our visitor entered warmer regions of space. By early September, something even more intriguing emerged. Hints of a greenish tint in some images of the comet's coma. Green comets aren't entirely unusual. The colour often comes from diatomic carbon molecules, C2, or sometimes from the same cyanide we'd already detected. but the specific source of 3I-ATLAS's green glow remained frustratingly unclear. Definitive spectroscopic confirmation of diatomic carbon would have to wait for more detailed observations. Meanwhile, a team of researchers submitted a preprint, an early research paper, not yet peer-reviewed, describing unusual polarization properties in light, reflecting from the comet's dust cloud. Polarization is a measure of how light waves are oriented, and it can tell us about the size, shape, and composition of dust particles. The preliminary results suggested something odd about the dust grains surrounding 3I-ATLAS, though exactly what remained unclear. Here's where we need to pump the brakes on speculation. Preprints are the academic equivalent of early drafts, important for sharing rapid results, but not yet vetted by the rigorous process of peer review. They represent hypotheses and preliminary data, not established facts. The polarization results, while intriguing, needed confirmation and careful analysis before drawing firm conclusions. What we definitely weren't seeing were the kinds of signals that would suggest artificial origin. No narrowband radio transmissions, no laser communications, no impossible maneuvers that would require rocket engines. The comet was following a perfectly natural trajectory dictated by gravity and the gentle pressure of solar radiation on its dust cloud. Scientists at NASA and elsewhere were quick to caution against leaping to extraordinary conclusions. Yes, 3I-ATLAS showed some unusual characteristics. Yes, it was behaving differently from solar system comets we'd studied before, but unusual and artificial are separated by a chasm of evidence that hadn't been bridged. The tendency to see patterns where none exist is a fundamental feature of human cognition. We're pattern-matching creatures, evolved to spot the tiger in the tall grass, even when it might just be shadows and wishful thinking. In astronomy, this instinct serves us well when identifying genuine phenomena, but it can also lead us astray when dealing with limited data and our own desire for cosmic significance. Still, there's something deliciously mysterious about an object that travels between the stars, carrying chemistry unlike anything in our local neighbourhood. Even if 3I-ATLAS turns out to be entirely natural, which remains the most likely explanation, it represents a sample of materials from somewhere else entirely, a messenger carrying news of conditions in stellar nurseries we'll never visit, around stars we can barely see. But what if, just for the sake of argument, we wanted to imagine something more deliberate behind its journey? What signs would we look for? What evidence would convince us we were dealing with intelligence rather than ice? Part 4. Signs of intelligence. If you were an alien intelligence planning to study a solar system undetected, how would you do it? The obvious answer, and the one favoured by science fiction, would be to build a massive mothership bristling with sensors and park it in orbit around the target planet. But that approach has a fatal flaw. It's rather hard to miss. A more subtle strategy might involve what researchers call lurker probes, artificial objects designed to blend in with natural phenomena. They'd be patient, quiet, and clever enough to masquerade as something ordinary, like, perhaps, a comet. This is pure speculation, of course. But it's not entirely unscientific speculation. The search for technosignatures, evidence of alien technology, has become a legitimate field of astronomical research, and interstellar objects, rare and exotic, represent natural candidates for closer scrutiny. So what would we look for in a genuine artificial visitor? First, anomalous accelerations. Any object moving through space is subject to predictable forces. Gravity, from the sun and planets, plus the gentle radiation pressure that pushes on dust and gas. If something were changing course without an obvious physical cause, speeding up, slowing down, or changing direction in ways that couldn't be explained by natural forces, that would raise serious questions. The previous interstellar visitor, Oumuamua, actually showed exactly this kind of behaviour. As it flew past the Sun in 2017, it accelerated slightly in a direction that couldn't be entirely explained by gravity alone. The effect was small but measurable, and it sparked years of scientific debate. Natural explanations exist, outgassing from hidden ice deposits, or even the possibility that Oumuamua was a fragment of solid hydrogen, but consensus remains elusive. Second, coordinated maneuvers. If an object were making purposeful changes to its trajectory, especially in response to planetary positions or solar activity, that would be difficult to explain naturally. Comets can show sudden changes in brightness or gas production as different types of ice are exposed to sunlight. but controlled course corrections would be another matter entirely. Third, structured emissions. Any advanced probe would presumably need to communicate with its builders, either to send back data or receive new instructions. We'd expect to see narrowband radio signals, laser communications, or other forms of artificial transmission. These would stand out against the broadband background of natural cosmic noise, like a violin solo in a thunderstorm. Fourth, thermal anomalies. Powered equipment generates waste heat, even in the cold of space. If something were running active sensors, computers, or communication systems, it would glow faintly in infrared wavelengths. Space telescopes equipped with thermal imaging could potentially detect artificial heat sources against the cold background of space. So far, 3I-ATLAS has shown none of these smoking gun indicators. Its trajectory follows the laws of celestial mechanics with boring predictability. No radio telescopes have detected artificial signals. No thermal cameras have spotted mysterious heat sources. If this is a probe, it's either powered down, extraordinarily well disguised, or operating in ways we haven't thought to monitor. But that doesn't stop us from examining the unusual features it does display. The polarization measurements, still awaiting peer review, suggest something odd about the dust particles in its coma. The chemical composition, dominated by carbon dioxide, differs significantly from typical solar system comets. Even the apparent sunward glow, brightness on the side facing our star, could be interpreted as evidence of active processes rather than simple thermal heating. Of course, each of these features has potential natural explanations. Polarization depends on dust, grain size and composition, which could vary dramatically between different stellar nurseries. Chemical ratios reflect formation conditions and the long journey through interstellar space. Sunward brightness can result from complex gas and dust dynamics. As a comet approaches perihelion, NASA scientists have been admirably careful to emphasize these natural alternatives. In a field where extraordinary claims require extraordinary evidence, they're right to counsel patience and skepticism. The history of astronomy is littered with initially mysterious phenomena that yielded to mundane explanations once better data became available. But here's the fascinating thing about technosignature research. Even negative results teach us something valuable. Every natural explanation we confirm, every ordinary comet we identify, helps us understand what genuine anomalies would look like. We're building a baseline of normal behavior against which truly unusual objects would stand out like cosmic sore thumbs. 2I divided by Borisov, the previous interstellar comet, provided exactly this kind of control case. It behaved like a perfectly prover. Ordinary comet throughout its visit, standard chemical composition, predictable brightening, normal dust production. If all interstellar visitors are variations on the same natural theme, then genuinely artificial objects should be recognizably different. Of course, there's another possibility we haven't considered yet. What if intelligence doesn't look like what we expect? What if the signs we're searching for, radio signals, heat sources, controlled maneuvers, represent our own technological biases rather than universal features of advanced civilizations? Maybe the universe is full of patient watchers who learned long ago that the best observation posts are the ones nobody notices. Maybe they've been drifting between stars for millions of years, collecting data on young civilizations like ourselves, waiting for the right moment to say hello. Or maybe, just maybe, they're already saying hello, and we haven't figured out how to listen. Part 5. First suspicion, watching us. Imagine you're walking through an African game preserve, and you notice something odd. The animals seem unusually calm. Predators ignore prey. Territorial disputes are minimal. Everything appears almost managed. You might begin to suspect that this isn't truly wild nature, but rather a carefully maintained environment where some unseen intelligence has established rules to keep the peace. Welcome to the zoo hypothesis, one of the more intriguing attempts to explain why the universe seems so quiet despite its obvious potential for life. The idea, first proposed in 1973 by MIT radio astronomer John Ball, suggests that advanced alien civilizations might operate under a galactic version of the Prime Directive. Just as we try to minimize our impact on wildlife preserves and indigenous cultures, perhaps spacefaring species have agreed to leave, developing civilizations alone. We're not being ignored, we're being protected. Under this scenario, Earth exists in a kind of cosmic nature preserve. We're free to evolve, to develop our own technology, to make our own mistakes, without interference from older, wiser civilizations. They watch from a respectful distance, taking notes, perhaps occasionally placing subtle limits on our expansion but never directly intervening. It's an appealing idea, especially when you consider the alternative possibilities. If the galaxy were truly wild, a free-for-all of competing civilizations, then younger species like ourselves might not survive their first contact with more advanced neighbors. The zoo model suggests a universe governed by ethics and restraint, where power comes with responsibility. But how would such a system work in practice? How do you monitor a civilization without being detected? One possibility involves what researchers call lurker probes, artificial objects placed in strategic locations to observe and report back to their builders. These wouldn't need to be massive constructions bristling with obvious technology. The most effective surveillance satellite would be the one that looked completely natural. Something small, patient, and clever enough to masquerade as space debris, asteroids, or, well, comets. Now, before we start fitting 3I-ATLAS for a tinfoil hat, let's be clear. There's no credible evidence that our interstellar visitor is anything other than a natural object. But the zoo hypothesis does provide an interesting lens through which to examine the broader question of cosmic silence. If advanced civilizations are out there but staying hidden, then occasional visitors from deep space might be our only glimpses of the larger galactic community. The beauty of using interstellar objects as camouflage is that they're naturally rare and exotic. Before automated sky surveys like ATLAS, we might have missed them entirely. Even now, with our best detection systems, we've confirmed only 3 interstellar visitors in 8 years. A civilization wanting to place long-term, observers in our solar system could hardly ask for better cover. Consider the operational advantages. An artificial probe disguised as a comet could drift through space for millions of years without raising suspicion. It could approach relatively close to inner planets during perihelion passages, gathering high-resolution data on atmospheric composition, industrial emissions, and signs of technological development. If questioned, it would appear to be exactly what it seemed, a chunk of ice and rock following natural orbital mechanics. The timing of 3I-ATLAS's arrival is, from this perspective, intriguing. We're living through what might be called humanity's great broadcasting period, the era when our radio and television signals first began leaking into space at detectable levels. We've also recently entered the space age, developed nuclear weapons, and begun serious discussions about interstellar travel. If you were monitoring a developing civilization, now might be an excellent time to take a closer look. But let's inject some healthy skepticism into this speculation. The Vera Rubin Observatory, currently under construction in Chile, will soon begin the legacy survey of space and time, a decade-long project that will photograph the entire southern sky every few nights. Current estimates suggest LSST could detect dozens or even hundreds of interstellar objects per year once it reaches full operation. If most of these turn out to be natural comets and asteroids, then 3I-ATLAS becomes considerably less special, just one sample from the ongoing exchange of material between stellar systems. The galaxy is probably full of ejected planetesimals drifting between stars, and we're only now developing the instruments sensitive enough to spot them regularly. The zoo hypothesis also faces a more fundamental challenge, the problem of consensus. For such a system to work, all spacefaring civilizations would need to agree to the same ethical framework. A single, aggressive species, the galactic equivalent of poachers, could disrupt the entire preserve. The fact that we haven't been contacted or conquered might simply mean that aggressive species are rare, not that protective species are common. Still, there's something almost comforting about the zoo model. It suggests we're not alone, but it also implies we're safe. Our cosmic neighbours, in this scenario, are patient gardeners rather than hungry predators. They're watching our development with the same mixture of concern and fascination that we feel when observing a nest of baby birds. Of course, there's a darker interpretation of cosmic silence. What if civilizations stay quiet not out of benevolence, but out of fear? What if the universe operates under harsher rules, where broadcasting your location is equivalent to painting a target on your world? This brings us to another possibility entirely, one that views interstellar space not as a peaceful preserve, but as a hunting ground where only the silent survive. But that's a story for the next chapter of our journey. For now, as 3I-ATLAS continues its quiet passage through our solar system, we're left with questions rather than answers. Are we witnessing the arrival of a natural visitor carrying samples from alien worlds? Or are we being studied by intelligence so subtle that we can't quite convince ourselves it exists? The universe, it seems, prefers to keep its secrets, at least for now. Part 6. The Great Silence Explained. Let's step back from our mysterious visitor for a moment and consider the bigger picture. The Fermi Paradox isn't just about one unusual comet. It's about the profound disconnect between what we'd expect from a galaxy teeming with life and what we actually observe. Nothing but cosmic silence. The numbers really are staggering when you sit down and work through them. Conservative estimates suggest our galaxy contains at least 100 billion stars. Many of these are similar to our Sun, burning steadily for billions of years. Recent discoveries by the Kepler Space Telescope and other planet-hunting missions suggest that roughly 1 in 5 Sun-like stars hosts an Earth-sized planet in its habitable zone, that sweet spot where liquid water can exist on the surface. Do the math, and you get roughly 10 billion potentially habitable worlds in our galaxy alone. Even if life is extraordinarily rare, arising on just one planet in a million, we should still have 10,000 civilizations in our cosmic neighborhood. But here's the kicker. Our galaxy is over 13 billion years old. Star formation began early in its history, meaning some stellar systems have had a several billion-year head start on us. If intelligent life developed elsewhere, even just 1% earlier than it did on Earth, those civilizations would have had tens of millions of additional years to develop technology, explore space, and leave detectable traces of their existence. With that much time, and that many potential starting points, the galaxy should be thoroughly explored by now. We should see signs of megastructures around distant stars, catch radio leakage from alien broadcasts, or at minimum detect the infrared waste heat from advanced civilizations consuming their star's energy output. Instead, we find silence. This cosmic quiet has spawned dozens of proposed solutions, but most fall into a few broad categories. Let's examine them like a detective reviewing case files, each offering a different answer to the central mystery. The rare Earth hypothesis suggests we're the winners of an incredibly unlikely lottery. Yes, planets are common, but Earth-like planets with stable climates, protective magnetic fields, large moons, and Jupiter-sized outer planets acting as cosmic vacuum cleaners might be extraordinarily rare. Add in the need for plate tectonics, the right atmospheric composition, and a host of other factors, and perhaps we're not just rare, we're unique. This solution has the advantage of requiring no assumptions about alien behavior or galactic politics. It simply proposes that the universe is harder to live in than we assumed, but it also implies a rather lonely cosmos, where consciousness might arise only once per galaxy, if at all. The Great Filter represents a more troubling possibility. Maybe intelligence isn't rare, but longevity, island. Perhaps there's some universal stumbling block that claims civilizations shortly after they reach technological adolescence. Nuclear weapons, climate change, artificial intelligence, or biotechnology gone wrong, some challenge that's simply too difficult for young civilizations to navigate. The terrifying version of this idea is that the filter lies ahead of us rather than behind us. Maybe developing spaceflight capabilities invariably leads to self-destruction. Maybe every civilization that reaches our current level of technological development has only decades or centuries left before something goes catastrophically wrong. But there are more optimistic interpretations of cosmic silence. Perhaps advanced civilizations simply have better things to do than broadcast their presence to the universe. Once you've solved the basic problems of energy, resources, and mortality, you might turn inward, exploring virtual realities, enhancing consciousness, or pursuing forms of art and philosophy that make interstellar communication seem primitive and pointless. This leads us to what we might call the transcendence hypothesis, the idea that sufficiently advanced civilizations graduate to forms of existence we wouldn't recognize as technological. They become something like cosmic hermits, so focused on internal development that they have little interest in galactic politics or exploration. Alternatively, maybe they're out there but staying deliberately quiet. The zoo hypothesis suggests benevolent supervision, older civilizations maintaining a hands-off policy toward younger species like ourselves. It's comforting to imagine wise, patient gardeners tending to the galaxy's development, but it requires remarkable restraint and consensus among species that might have very different values and motivations. The dark forest hypothesis offers a grimmer take on deliberate silence. Proposed by Chinese science fiction author Liu Cixin, it suggests that the universe operates under the logic of a dark forest, where revealing your location brings swift destruction from competitors. Every civilization faces a terrible choice: remain hidden and survive, or broadcast your presence and risk annihilation by someone more powerful. Under this model, the galaxy could be full of civilizations, all hiding in fearful silence, afraid to make the first move that might expose them to cosmic predators. It's a paranoid universe, where first contact means first strike capability. Then there are the technical solutions, possibilities that focus on how we're searching rather than what we might find. Maybe alien communications use technologies we haven't invented yet, quantum entanglement, gravitational waves, or forms of physics we don't yet understand. We're like someone trying to detect cell phone conversations using a telegraph key, looking for the right thing in the wrong way. Or perhaps the signals are there, but they're brief, directional, or encoded in ways that make them nearly impossible to distinguish from natural phenomena. A truly advanced civilization might use communication methods so efficient that their signals would be invisible to anyone lacking the proper decoding algorithms. This is where our interstellar visitors become particularly interesting. Even if they're entirely natural, comets like 3I-ATLAS represent a form of cosmic communication, not intentional messages, but samples of chemistry and physics from other stellar systems. They're letters in bottles, carrying information about conditions around distant stars and the processes that shape planetary formation. By studying the compositions, sizes, and behaviors of interstellar objects, we're essentially conducting a form of archaeology, examining the debris left behind by solar system formation processes throughout our galactic neighborhood. Each visitor tells us something about the materials available for planet formation, the dynamics of stellar evolution, and the kinds of environments where life might or might not take hold. In this sense, 3I-ATLAS doesn't need to be artificial to be significant. Whether it's a natural comet or something more exotic, it represents our most direct sampling of conditions beyond our solar system. It's a messenger from the cosmic deep, carrying news of worlds we may never visit. But as we'll see next, this visitor isn't our first interstellar guest, and the stories told by its predecessors are equally fascinating, if in very different ways. Part 8. Historical Echoes of Visitors. To understand what makes 3I-ATLAS special, we need to meet its predecessors, the only other confirmed visitors from beyond our solar system. Each tells a different story about the space between the stars, and together they're beginning to sketch the first crude portrait of our galactic neighborhood. The first interstellar object ever confirmed, 1I, Oumuamua, arrived like a cosmic mystery novel. Discovered on October 19, 2017, by the Pan-STARRS telescope in Hawaii, it initially appeared to be an asteroid, a bare rock tumbling through space without the gas and dust coma typical of comets. But Oumuamua was strange from the start. Its shape was utterly unlike anything we'd seen in our solar system, extremely elongated, perhaps 10 times longer than it was wide, like a cosmic cigar or pancake spinning end over end. Its surface was surprisingly reflective, almost metallic in appearance, and it showed dramatic variations in brightness as it rotated, suggesting either an extremely elongated shape or unusual surface properties. More puzzling still was its motion. As Oumuamua swung around the sun and headed back toward interstellar space, it accelerated slightly in a direction that couldn't be entirely explained by gravitational forces alone. The effect was small but measurable, about what you'd expect from a gentle rocket push or from gas jetting off a comet's surface. The problem was, nobody could see any gas. This non-gravitational acceleration sparked years of scientific debate and increasingly exotic explanations. Maybe Oumuamua was venting hydrogen gas, invisible to our instruments. Maybe it was a fragment of a hydrogen iceberg, slowly sublimating in the sun's heat. Some researchers even suggested it might be an artificial light sail, pushed by solar radiation pressure, though this idea required Oumuamua to be extraordinarily thin and lightweight. The controversy highlighted a fundamental challenge in studying interstellar objects. They don't stick around. By the time we realize what we're looking at, they're already on their way out of the solar system, moving too fast and getting too faint for detailed follow-up observations. Oumuamua became invisible to ground-based telescopes within months of its discovery, leaving behind more questions than answers. The second confirmed interstellar visitor couldn't have been more different. 2I divided by Borisov, discovered on August 30th, 2019, by amateur astronomer Gennady Borisov, using a homemade telescope in Crimea, behaved exactly like what astronomers expected an interstellar comet to be. From the moment of its discovery, Borisov displayed a classic coma and tail. As it approached the Sun, it brightened predictably, developed an increasingly prominent dust trail, and showed all the chemical signatures of a typical comet: water vapor, carbon monoxide, and dust particles creating a glowing envelope around its nucleus. Spectroscopic analysis revealed a refreshingly familiar composition. The ratio of water to carbon monoxide in Borisov's coma matched values seen in many solar system comets. Its dust properties, grain sizes, and gas production rates all fell within the range of normal cometary behavior. Even its nucleus size, estimated between 100 meters and a few kilometers across, was perfectly ordinary. In scientific terms, Borisov was almost boring, and that was wonderful. You see, Borisov provided something invaluable: a control case. It showed us what a normal interstellar comet looks like, establishing a baseline against which future visitors could be compared. If all interstellar objects were as mysterious as Oumuamua, we might start to suspect that the space between stars operated under different physical laws. Borisov proved that at least some interstellar wanderers are exactly what they appear to be: chunks of ice and rock following predictable physics. The comet's origin story was equally straightforward. Backtracking its trajectory through space, astronomers determined that Borisov likely came from the direction of the constellation Cassiopeia, possibly ejected from its birth system by gravitational interactions with giant planets. It had been travelling through interstellar space for millions of years before entering our solar system, carrying with it samples of materials from its distant homeland. During its closest approach to the Sun in December 2019, multiple space telescopes trained their instruments on this cosmic visitor. Hubble captured detailed images of its nucleus and coma structure. Ground-based observatories measured its chemical composition and dust properties. The European Southern Observatory's Very Large Telescope tracked changes in its brightness and activity levels. The data confirmed what initial observations suggested. 2I divided by Borisov was remarkably similar to comets born in our own solar system, despite travelling from an entirely different stellar neighbourhood. This similarity suggested that the basic processes of planet formation, the condensation of ice and dust in cold outer regions of stellar systems, might be remarkably universal. But the discovery also raised intriguing questions about galactic chemistry. If comets from different star systems show similar compositions, what does that tell us about the materials available for planet formation throughout our region of the galaxy? Are the building blocks of life, water, carbon compounds, organic molecules, distributed fairly uniformly among stellar systems? Or was Borisov's apparent familiarity misleading, masking subtle differences that could reveal important details about its origin? These questions became more pressing with the arrival of our third confirmed visitor. 3I-ATLAS, as we've seen, displays comet-like activity similar to Borisov, but with chemical composition that's distinctly different from either typical solar system comets or its immediate predecessor. The pattern emerging from our small sample of interstellar visitors is intriguing. One mysterious and inactive, one Oumuamua, one familiar and well-behaved, 2I divided by Borisov, and now one that's active but chemically unusual. 3I-ATLAS. It's like meeting three strangers from the same distant city and finding that each has a completely different personality. The rarity of these encounters makes each one precious. In the 8 years since Oumuamua's discovery, we've confirmed only 3 interstellar objects, despite increasingly sophisticated sky surveys. The Vera Rubin Observatory, when it begins operations, is expected to find dozens per year, transforming interstellar visitors from rare curiosities into a regular part of astronomical research. But for now, we're still in the early days of interstellar archaeology. Each visitor provides a unique sample of conditions elsewhere in the galaxy, a snapshot of chemistry and physics from stellar systems we may never be able to visit directly. They're like core samples from the cosmic deep, carrying information about planet formation, stellar evolution, and the distribution of materials throughout our galactic neighbourhood. The controversy surrounding Oumuamua also taught us important lessons about the scientific process. Initial mystery doesn't necessarily imply exotic explanations. Better data and more sophisticated models often resolve apparent anomalies without requiring revolutionary new physics or, for that matter, alien artifacts. As we've refined our understanding of how objects behave in the outer solar system, we've developed better tools for distinguishing between genuinely unusual phenomena and the normal complexity of celestial mechanics. Non-gravitational accelerations, for instance, can result from several natural processes: asymmetric outgassing, changes in shape due to sublimation, or even the gradual loss of surface material under solar heating. This improved understanding makes the features of 3I-ATLAS more interesting, not less. Its unusual chemical composition can't be easily dismissed as an observational artifact or modelling error. The high ratio of carbon dioxide to water vapour represents a genuine difference from both solar system comets and 2I divided by Borisov. Whether this difference reflects formation conditions in its birth system, modifications during its long journey through interstellar space, or something else entirely remains an open question. But it's exactly this kind of question that makes interstellar visitors so valuable for astronomy. They provide natural experiments in comparative planetology, allowing us to study the results of planet formation processes under different conditions and in different environments. And occasionally, they force us to confront more speculative possibilities. If intelligence were watching our solar system, how would it do so without being detected? Part 9. Evidence of the Watcher. Let's examine the evidence surrounding 3I-ATLAS with the methodical care of investigators processing a crime scene, not because we suspect criminal activity, but because extraordinary claims require extraordinary scrutiny, and some of the claims swirling around our interstellar visitor have been quite extraordinary indeed. First, the polarization measurements. A team of researchers published preliminary results suggesting that light reflected from 3I-ATLAS's dust cloud shows unusual polarization properties. Polarization is essentially a measure of how light waves are oriented, whether they vibrate in random directions or show preferential alignment. For most comets, polarization measurements help us understand the size, shape, and composition of dust particles in the coma. The preliminary data suggested negative polarization at certain viewing angles, which is uncommon but not unprecedented in solar system objects. What made it interesting was how different the pattern appeared compared to typical comets. However, and this is crucial, these results were published as a preprint, meaning they haven't yet undergone the rigorous peer review process that validates scientific findings. Preprints serve an important function in astronomy, allowing rapid sharing of time-sensitive observations, but they're also preliminary by definition, subject to revision, correction, or even retraction as more data becomes available. The polarization measurements of 3I-ATLAS remain intriguing but unconfirmed. Meanwhile, Hubble's sharp vision revealed the comet's morphology in exquisite detail. The images showed a classic teardrop-shaped dust envelope, with material being swept away from the nucleus by solar radiation pressure. The symmetry and behavior of this dust cloud followed exactly the patterns predicted by standard comet physics. Solar heating vaporizes ice, gas drags dust particles along, and radiation pressure pushes the debris into a tail pointing away from the sunday. Nothing about the structure suggested artificial origin or controlled processes. It looked, quite simply, like a comet doing comet things. The James Webb Space Telescope provided, perhaps, the most significant findings. JWST's infrared spectroscopy revealed that unusual chemical composition we discussed earlier, a carbon dioxide to water vapor ratio of roughly 8:1, among the highest ever measured in any comet. Additional gases detected included carbon monoxide, carbonyl sulfide, and various organic compounds, painting a picture of an object rich in carbon-bearing molecules. This chemistry tells a story about formation conditions. Water ice condenses at higher temperatures than carbon dioxide ice, so a CO2 rich composition suggests formation in an extremely cold environment, or perhaps selective loss of water during the long journey through interstellar space. Neither scenario requires intelligence, just unusual physics or chemistry. Ground-based telescopes added their own pieces to the puzzle. Detection of hydrogen cyanide began in late August, with production rates increasing as the comet approached the sunday. The timing made perfect sense. Different types of ice, sublime at different temperatures, so we'd expect to see various gases appear in sequence as solar heating penetrated deeper into the nucleus. By early September, some images began showing hints of green coloration in the comet's coma. Green comets aren't unusual. The color typically comes from diatomic carbon molecules or cyanide fluorescence. But definitive identification of the specific molecules responsible required more detailed spectroscopy than was initially available. Size estimates remained frustratingly uncertain. The growing coma increasingly obscured the nucleus, making it difficult to determine whether we were looking at a large object with low activity or a small object punching above its weight. Current estimates place the nucleus diameter somewhere between 320 meters and 5.6 kilometers, a range that encompasses everything from a city block to a small mountain. Now, here's where we need to address some of the more sensational claims that appeared in media coverage. Various outlets suggested that 3I-ATLAS was half the size of the Sun, or showed other impossible characteristics. These claims appear to have confused the size of the comet's expanding coma, which can indeed grow to enormous dimensions, with the size of the solid nucleus at its center. The coma is mostly empty space, with tiny dust particles scattered throughout. Saying it's huge is like claiming that fog is solid because you can see it from miles away. The actual comet, the rocky, icy nucleus, remains quite small by astronomical standards. Similarly, some reports described mysterious sunward glows or anti-tail features as evidence of artificial propulsion or controlled emissions. In reality, these phenomena can result from natural dust dynamics. Particles of different sizes are pushed by solar radiation at different rates, creating complex structures that can appear to point in unexpected directions depending on viewing angle and timing. NASA scientists were admirably clear in their public statements. Based on current evidence, 3I-ATLAS appears to be a natural comet following predictable physics. While they acknowledged its unusual characteristics, particularly the chemistry, they found no credible evidence of artificial origin or controlled behavior. This brings us to a crucial point about the search for technosignatures. If an advanced civilization were operating stealth probes in our solar system, what would we expect to detect? Most likely some form of artificial signal, narrowband radio transmissions, laser communications, or modulated light curves that couldn't be explained by natural processes. We might also expect thermal signatures from powered equipment, unusual accelerations from propulsion systems, or coordinated maneuvers in response to planetary positions or solar activity. Advanced materials might show spectroscopic signatures unlike anything in natural mineralogy. None of these smoking guns have been detected around 3I-ATLAS. Radio telescopes monitoring the object have found no artificial transmissions. Infrared observations show thermal emission consistent with solar heating of natural materials. The comet's trajectory follows the laws of celestial mechanics without requiring thrust or course corrections. If this is a probe, it's either completely powered down, operating in ways we haven't thought to monitor, or using technology so advanced that it's indistinguishable from natural phenomena. Any of these possibilities would make detection extraordinarily difficult with current instruments, but perhaps we're asking the wrong question. Instead of looking for obvious signs of intelligence, maybe we should consider more subtle possibilities. What if advanced civilizations have learned that the best surveillance is the kind that looks entirely natural? What if patience, rather than technology, is the mark of true cosmic sophistication? Why remain silent? If intelligence exists elsewhere in the galaxy, and the math suggests it almost certainly does, then why haven't we heard from anyone? The question assumes that advanced civilizations would want to communicate, but perhaps that assumption reveals more about human nature than cosmic reality. Consider what we know about intelligence here on Earth. The most successful species aren't necessarily the loudest ones. Humans dominated the planet not through roaring and chest beating, but through cooperation, planning, and the patient accumulation of knowledge. Maybe cosmic intelligence follows similar patterns, favoring subtlety over spectacle. The zoo hypothesis, which we touched on earlier, suggests that advanced civilizations operate under a kind of galactic prime directive, a commitment to non-interference with developing worlds. Under this model, we're living in a carefully maintained preserve, studied but not contacted, protected but not controlled. The logic is compelling from an ethical standpoint. If you're thousands or millions of years more advanced than a developing civilization, direct contact would be inherently disruptive. Your mere presence would alter their natural development, potentially stunting their growth or creating harmful dependency. Better to watch from a distance, letting them find their own path to cosmic citizenship. This approach would require remarkable patience and coordination among spacefaring species. Every advanced civilization in our galactic neighborhood would need to agree to the same hands-off policy, A single aggressive or careless species could disrupt the entire system. But perhaps that's exactly what we'd expect from truly mature civilizations, the wisdom to recognize that diversity of development is more valuable than rapid expansion. The zoo hypothesis also explains why contact might be delayed rather than permanently avoided. Young civilizations need time to develop their own values, technologies, and approaches to cosmic citizenship. Once they reach sufficient maturity, perhaps marked by achieving interstellar travel, solving energy and resource challenges, or demonstrating stable governance, the quarantine might be lifted. From this perspective, our current historical moment becomes particularly interesting. We're living through humanity's transition from a single-planet species to a spacefaring civilization. We've developed nuclear weapons, begun exploring our solar system, and started broadcasting our presence through radio and television signals. If cosmic neighbours were waiting for signs of technological adolescence, this would be exactly the era when they'd pay closer attention. But there's a darker interpretation of cosmic silence. Liu Cixin's dark forest hypothesis suggests that the universe operates under harsher rules, where revealing your location is tantamount to signing your own death warrant. The logic here is grimly Darwinian. In a galaxy full of civilizations competing for resources, first contact often means first strike capability. If you discover another civilization, you face a terrible choice: destroy them before they can threaten you, or risk being destroyed when they eventually develop superior technology. The only safe strategy is to remain hidden, eliminating threats while staying invisible yourself. Under this model, the galaxy could be full of civilizations, all hiding in fearful silence. Broadcasting your presence, as we've been inadvertently doing through radio and television leakage, would be like lighting a campfire in a forest full of hungry predators. Eventually, something would come calling, and the encounter wouldn't be friendly. The dark forest hypothesis explains not just silence, but active elimination of detected civilizations. Any species that reveals itself through radio signals, megastructures, or other detectable activities gets added to someone else's target list. The universe becomes a cosmic horror story, where paranoia is the price of survival. Both hypotheses, benevolent zoo and malevolent forest, make testable predictions about what we might observe. Zookeepers might use subtle surveillance methods, like natural-looking probes disguised as asteroids or comets. Their technology would be sophisticated enough to avoid detection while gathering detailed information about developing civilizations. Dark forest predators, on the other hand, might focus on rapid detection and elimination systems. They'd want to identify emerging civilizations as quickly as possible before those civilizations could develop defensive capabilities or escape to other star systems. Neither scenario provides much comfort for a young civilization like ourselves. Zoo dwellers face an indefinite period of isolation and uncertainty, never knowing when or if contact will be permitted. Dark forest inhabitants live under constant threat of annihilation from neighbours they can't see or predict. But there are other possibilities that don't require either benevolent, supervision, or malevolent competition. Maybe advanced civilizations simply have better things to do than worry about galactic politics. Consider the trajectory of human interests over recorded history. Our ancestors were primarily concerned with immediate survival, finding food, avoiding predators, securing shelter. As societies became more sophisticated, we developed interests in art, philosophy, and abstract knowledge. The most advanced human cultures often turn inward, focusing on psychological and spiritual development rather than territorial expansion. Perhaps cosmic civilization follows a similar pattern. Once you've solved the basic problems of energy, resources, and mortality, you might lose interest in exploring or communicating with primitive neighbours. Why waste time on interstellar radio when you could be exploring the depths of consciousness, creating virtual realities more complex than entire galaxies, or pursuing forms of art and science that we can't even imagine? This transcendence hypothesis suggests that sufficiently advanced civilizations graduate beyond physical reality as we understand it. They become cosmic hermits, so focused on internal development that external universe becomes irrelevant. From our perspective, such civilizations would be effectively invisible. They'd use minimal physical resources, produce no detectable waste products, and show no interest in expansion or communication. They might exist all around us, in virtual realities, alternate dimensions, or states of being that our science can't yet detect or comprehend. The implications of each model are profound for how we should conduct ourselves as we mature as a civilization. If we're in a zoo, then demonstrating wisdom, restraint, and ethical development might be the key to eventual contact. If we're in a dark forest, then developing defensive capabilities and maintaining radio silence might be essential for survival. If advanced neighbors have transcended physical concerns, then our own path toward cosmic citizenship might involve similar inward development. But perhaps the most honest answer is that we simply don't know enough to choose among these possibilities. The universe is under no obligation to conform to human expectations or preferences. Reality might be stranger, more complex, or more mundane than any of our current models suggest. What we can say is that the search itself has value, regardless of what we find. Every attempt to understand cosmic silence teaches us something about the nature of intelligence, the requirements for technological civilization, and our own place in the grand scheme of things. And occasionally, that search is enriched by visitors like 3I-ATLAS, messengers from the cosmic deep, that force us to refine our questions about who might be out there and what they might want with a young civilization learning to reach for the stars. Part 10. The Window of Opportunity. Time is running short for detailed observations of our interstellar visitor. As October advances toward 3I-ATLAS's closest approach to the Sun, astronomers around the world are racing to gather as much data as possible before the comet begins its journey back to the interstellar darkness. The timeline is both exciting and frustrating. Perihelion, the point of closest approach to our star, will occur around October 29th or 30th, depending on precise orbital calculations that are still being refined. At that moment, 3I-ATLAS will be approximately 1.4 astronomical units from the Sun, or about 210 million kilometers away. This is close enough for the Sun's radiation to fully activate any remaining ice deposits in the comet's nucleus, potentially revealing new chemical components that haven't yet been detected. Different types of ice, sublime at different temperatures, so perihelion passage often brings surprises, as deeper layers of the nucleus are exposed to solar heating for the first time. For Earth-based observers, the geometry becomes increasingly favorable through October. While 3I-ATLAS will never approach closer than 1.8 astronomical units from our planet, a comfortably safe distance of roughly 270 million kilometers, this represents the optimal balance between proximity and observing conditions. The comet's apparent brightness is expected to peak around perihelion, though predictions remain uncertain. Current estimates suggest it will reach somewhere between 8th and 10th magnitude, far too faint for naked eye observation, but well within range of moderate-sized telescopes. Amateur astronomers with decent equipment and dark skies might be able to spot it as a fuzzy star-like object, though the real scientific value lies in professional observations using sophisticated instruments. Multiple space-based observatories are coordinating their efforts to maximize scientific return during this narrow window of opportunity. The Hubble Space Telescope continues to monitor the comet's morphological evolution, tracking changes in the size and structure of its coma as gas production varies with solar heating. These observations help astronomers understand the nucleus composition and how material is being lost as the comet approaches the Sunday. The James Webb Space Telescope provides unparalleled infrared spectroscopy, capable of detecting trace gases that might be invisible to ground-based instruments. JWST's sensitivity allows it to measure not just the major chemical components like carbon dioxide and water vapor, but also exotic molecules that could reveal important details about formation conditions in the comet's birth system. Ground-based observatories are contributing their own specialized capabilities. Radio telescopes monitor for any artificial signals, though none have been detected to date. Polarimetric observations continue to probe the properties of dust particles in the comet's coma, potentially revealing information about grain sizes, composition, and surface textures that reflect conditions in distant protoplanetary disks. Several research teams are preparing rapid response observation campaigns for any sudden changes in the comet's behavior. Comets can be unpredictably dynamic objects, especially when approaching close to the Sunday. Sudden outbursts of gas or dust, changes in rotation rate, or even fragmentation events are all possibilities that could dramatically alter the comet's appearance over short timescales. The flood of data being generated presents its own challenges. Multiple research groups are publishing preliminary results as preprints, sharing their findings with the broader scientific community before formal peer review. This approach allows for rapid dissemination of time-sensitive observations, but it also means that early results should be interpreted cautiously until they've undergone rigorous scientific scrutiny. The peer review process, while essential for validating scientific findings, typically takes months to complete. By the time formal papers are published, 3I-ATLAS will likely have faded beyond the detection limits of most telescopes. This creates tension between the need for rapid sharing of results and the requirement for careful verification of claims. Looking toward the future, observations of 3I-ATLAS are providing valuable experience for studying the much larger population of interstellar objects that will be discovered by next-generation surveys. The Vera Rubin Observatory, currently under construction in Chile, is expected to begin operations within the next few years. Its large synoptic survey telescope will photograph the entire southern sky every few nights, potentially detecting dozens of interstellar visitors annually. This dramatic increase in discovery rate will transform interstellar objects from rare curiosities into a regular subject of astronomical research. We'll be able to study them statistically, looking for patterns in their compositions, sizes, and behaviors that could reveal important information about planet formation processes throughout the galaxy. The Nancy Grace Roman Space Telescope, scheduled for launch later this decade, will add infrared capabilities that complement ground-based surveys. Its wide-field observations will be particularly valuable for detecting faint interstellar objects and tracking their evolution over time. But these future capabilities make current observations of 3I-ATLAS all the more precious. We're still in the era when each interstellar visitor represents a significant scientific event, deserving of intensive study with our best available instruments. The detailed characterization we're conducting now will provide baseline data for understanding the broader population of objects we expect to discover in coming years. There's also the possibility, remote but tantalizing, that 3I-ATLAS might reveal something genuinely unexpected during its perihelion passage. Comets have surprised astronomers before with sudden outbursts, unusual spectroscopic features, or behavioral changes that challenge our understanding of how these objects work. If 3I-ATLAS were to show signs of artificial origin or controlled behavior, perihelion would be the most likely time for such evidence to emerge. The increased solar heating and enhanced observational opportunities create optimal conditions for detecting any anomalies that might distinguish an artificial object from a natural one. Of course, the most probable outcome remains that 3I-ATLAS will continue to behave like an unusual but entirely natural comet. Its high carbon dioxide content and distinctive chemistry will provide valuable insights into conditions around distant stars, but won't require revolutionary new explanations or invoke the possibility of alien intelligence. Either way, we're witnessing a rare and precious event, the passage of a messenger from the cosmic deep through our local solar system. Whether that messenger carries only chemical information about its distant birthplace or something more extraordinary remains to be determined, but the window of opportunity is closing. Within months, 3I-ATLAS will begin its long journey back to interstellar space, carrying its secrets toward encounters with other stellar systems we can only imagine. Time will tell whether we've made the most of this cosmic appointment. Part 11. If it's alive. Let's indulge in a thought experiment that pushes the boundaries of conventional thinking. What if, instead of being merely a chunk of ice and rock, 3I-ATLAS represents something more exotic, a form of life adapted to the extreme conditions of interstellar space? Before you dismiss this as pure science fiction, consider that life on Earth has surprised us repeatedly with its tenacity and adaptability. We've found organisms thriving in boiling hot springs, inside solid rock kilometers below the surface, in the most acidic and alkaline environments imaginable, and even in the vacuum of space itself. Tardigrades, microscopic water bears, can survive direct exposure to cosmic radiation and the harsh environment beyond our atmosphere. If life can adapt to such extremes on a single planet, who's to say it couldn't evolve to survive in the cold, sparse conditions of interstellar space? Imagine a form of chemistry that operates at temperatures just a few degrees above absolute zero, using the sparse hydrogen and cosmic dust of interstellar medium as its basic building blocks. Such organisms, if we can call them that, might exist as vast, distributed networks of chemical reactions, taking millions of years to complete what we would consider basic metabolic processes. The energy sources in interstellar space are admittedly limited. Cosmic ray radiation, the faint glow of distant stars, and occasional gravitational interactions might provide the minimal energy needed to sustain extremely slow chemical processes. A living interstellar object might operate more like a vast chemical computer than anything we'd recognize as biological, processing information and responding to environmental changes over geological timescales. Such an entity might incorporate solid materials, ice, rock, and organic compounds as structural components while maintaining its essential character as a self-organizing chemical system. From the outside, it might appear indistinguishable from a natural comet or asteroid. Only detailed analysis of its behavior might reveal the subtle patterns that indicate internal organization rather than simple physics. Now, to be absolutely clear, there's no evidence whatsoever that 3I-ATLAS represents any form of life. Its chemical composition, thermal behavior, and response to solar heating all fall within the range expected for natural comets. The carbon dioxide-rich environment and emerging cyanide detections can be explained entirely through conventional ice chemistry and solar heating. But the exercise of imagining living interstellar objects isn't entirely frivolous. It forces us to think more carefully about what we mean by life and what kinds of signatures we should look for when searching for biology beyond Earth. Traditional definitions of life typically include requirements for metabolism, growth, reproduction, and response to environmental stimuli. But these definitions are based on the only example we know: carbon-based, water-dependent biochemistry, operating within a narrow range of temperatures and pressures found on Earth's surface. Life that evolved in the cosmic deep might operate under entirely different principles. Instead of discrete organisms, we might be dealing with distributed systems that exist as patterns in chemistry and physics, rather than as distinct physical entities. Instead of rapid growth and reproduction, we might see gradual organizational changes that unfold over millions of years. Such life might respond to environmental falls, changes, like approaching a star system, in ways that could appear to be intelligent behavior, even if no consciousness or intentionality were involved. Complex chemical systems can exhibit emergent properties that look like purpose or planning, while operating entirely through natural selection and self-organization. This brings us to a crucial point about the search for extraterrestrial life. We're naturally biased toward looking for biology that resembles our own, operating on timescales and energy levels familiar from terrestrial experience. But the universe is under no obligation to conform to our expectations or limitations. If 3I-ATLAS was somehow alive, which, again, remains pure speculation, it might represent a form of biology so different from earthly life that we wouldn't recognize it as such, even if we were staring directly at the evidence. Its metabolic processes might operate too slowly for us to detect. Its reproductive strategies might involve mechanisms we haven't thought to monitor. Its responses to environmental stimuli might be too subtle or too alien for our instruments to interpret correctly. The chemistry we're observing, high carbon dioxide content, emerging cyanide, complex organic compounds, could theoretically support exotic biochemical processes under the right conditions. Carbon dioxide can participate in a wide variety of chemical reactions, especially in the presence of other carbon-bearing molecules and appropriate catalysts. Cyanide, despite its toxic reputation on Earth, is actually a common component in the chemistry of star formation and might play important roles in non-terrestrial biochemical systems. Even the comet's physical structure, a nucleus surrounded by an expanding cloud of gas and dust, bears some resemblance to cellular organization, albeit on an enormous scale. The nucleus could function as a kind of core processing unit, while the coma serves as an extended metabolic system where chemical reactions take place, in the tenuous but vast atmosphere surrounding the central body. Of course, these analogies can be pushed too far. The apparent similarities between cometary structure and cellular organization are almost certainly coincidental, the result of similar physical processes, centralized mass with dispersed atmosphere, rather than evolutionary relationships. But the exercise reminds us that life might take forms we haven't imagined, operating in environments we consider impossibly hostile using chemistry we don't fully understand. The discovery of extremophiles on Earth, organisms thriving in conditions that would instantly kill most life forms, has repeatedly expanded our understanding of biology's possibilities. Perhaps more importantly, considering the possibility of exotic life forms helps us recognize our own assumptions and biases when interpreting astronomical observations. The line between complex chemistry and simple biology isn't always clear, especially when dealing with systems operating on scales and timescales far removed from terrestrial experience. If we were to detect genuinely living interstellar objects, the implications would be staggering. It would suggest that life isn't confined to planetary surfaces, but might exist throughout the galaxy as a distributed cosmic-scale phenomenon. The space between stars, rather than being empty and lifeless, might teem with exotic biology adapted to conditions we're only beginning to understand. Such a discovery would revolutionize our understanding of life's possibilities and dramatically increase the odds that intelligence might evolve in environments we'd never considered habitable. It would also provide new insight into the Fermi Paradox. Perhaps advanced civilizations aren't hiding on planets, but have learned to exist as distributed entities operating on galactic scales. But we're getting ahead of ourselves. The evidence from 3I-ATLAS, while fascinating, points toward natural but unusual chemistry, rather than biology of any kind. The comet's behavior can be explained through conventional physics without invoking exotic life forms or artificial intelligence. Which brings us to our next thought experiment. What if 3I-ATLAS isn't alive but isn't entirely natural either? Part 12. If it's a probe. The concept of interstellar probes disguised as natural objects has a long and respectable history in both scientific speculation and science fiction. The idea is elegantly simple. If you want to study a developing civilization without being detected, you design your surveillance equipment to look like something completely ordinary. A comet makes perfect camouflage. It's expected to be inactive during most of its journey through space, becoming active only when heated by solar radiation. It follows predictable orbital mechanics. Its composition and behavior can be explained through well-understood physical processes. Most importantly, it's rare enough that detailed study of every interstellar visitor would be justified on purely scientific grounds, providing excellent cover for more thorough observation. So let's imagine, purely as a thought experiment, that 3I-ATLAS is exactly this kind of stealth probe. What would we expect to see, and how would it differ from a natural comet? First, consider the operational requirements. A probe designed to study our solar system would need sensors capable of analyzing planetary atmospheres, detecting industrial emissions, and measuring electromagnetic radiation from technological civilizations. It would need data storage systems to record observations over potentially decades or centuries. It would need communication systems to transmit findings back to its builders, though these transmissions might be delayed until the probe reached a safe distance from the target system. All of this equipment would require power. Solar panels could provide energy when close to a star, but would be useless during the long journey through interstellar space. Nuclear power sources might be necessary, but would generate detectable heat signatures. The most sophisticated approach might involve some form of highly efficient energy storage or conversion system that we haven't yet developed. The probe would also need to maintain its disguise throughout its mission. This means behaving exactly like a natural comet when observed with contemporary instruments, while secretly conducting much more detailed observations than any comet should be capable of making. Now, what signs might betray such a sophisticated deception? The most obvious signature would be artificial transmissions. Any probe would presumably need to communicate with its builders, either to receive new instructions or to transmit collected data. These signals might be highly directional, transmitted only when the probe is oriented correctly relative to its home system, or they might use communication technologies we don't yet understand. We might also expect to see subtle deviations from purely natural behavior. Natural comets respond to solar heating in predictable ways, but a probe might need to adjust its position or orientation to optimize its sensor coverage. These maneuvers would need to be gentle enough to appear natural, perhaps disguised as normal outgassing or rotation changes. Thermal signatures could also reveal artificial systems. Electronic equipment generates waste heat, even when operating at high efficiency. A probe conducting active sensing might show thermal patterns inconsistent with simple solar heating, especially if it were using power-hungry sensors or communication systems. More subtly, we might detect signs of artificial materials or unusual structural organization. Natural comets are essentially rubble piles, loose aggregations of ice, rock, and dust, held together by weak gravity. A probe would need more sophisticated internal structure to house and protect sensitive equipment, which might be detectable through EDGE, detailed gravitational analysis or seismic studies, if the object were to be visited by a spacecraft. So how does 3I-ATLAS measure against these criteria? Radio telescopes have monitored the comet for artificial transmissions and found none. The Very Large Array, Arecibo successor facilities, and other sensitive instruments have detected no narrowband signals, no modulated transmissions, no signs of artificial communication. If the object is transmitting, it's either using technologies we don't monitor or directing its signals away from Earth. Thermal observations show emissions consistent with solar heating of natural materials. The temperature distribution across the comet's nucleus and coma matches what we'd expect from ice sublimation and dust heating, without obvious signs of internal power sources or active equipment. The object's trajectory follows the laws of celestial mechanics with boring predictability. No course corrections, no attitude adjustments, no maneuvers that would suggest active control systems. It's moving exactly as we'd expect for a natural object under the influence of gravity and radiation pressure. Even the unusual chemical composition, high carbon dioxide, emerging cyanide, complex organics, can be explained through natural processes without invoking artificial systems. Different stellar environments produce different chemical compositions, and the long journey through interstellar space could modify a comet's original chemistry through cosmic ray bombardment and selective sublimation. But here's where the probe hypothesis becomes really interesting. A truly sophisticated stealth system might be designed to pass exactly these kinds of tests. If you're thousands of years more advanced than the civilization you're studying, creating perfect natural camouflage might be a relatively simple engineering challenge. Consider the level of technology required. You'd need materials that perfectly mimic the spectroscopic signatures of natural ice and rock. You'd need power systems that produce no detectable waste heat, or that can perfectly simulate the thermal signature of solar heating. You'd need propulsion systems so subtle that they're indistinguishable from natural outgassing, yet precise enough to make minor course corrections over years or decades. Most challenging of all, you'd need to predict what kinds of tests the target civilization might apply. Your probe would need to fool not just current instruments, but also more advanced sensors that might be developed during its mission. It would need to be sophisticated enough to adapt its camouflage as detection methods improved. From this perspective, the very fact that 3I-ATLAS appears completely natural might be the most sophisticated technology of all. A probe designed by a civilization capable of interstellar travel would presumably be smart enough to avoid the obvious mistakes that would reveal its artificial nature to primitive observers like ourselves. But we're walking into a logical trap here. If we assume that any natural-appearing object might be artificial, then we've made the hypothesis unfalsifiable. Every natural behavior becomes evidence of sophisticated camouflage. Every chemical signature becomes proof of advanced material science. Every orbital trajectory becomes evidence of perfect gravitational calculation. Science works by testing hypotheses that make specific, testable predictions. The probe hypothesis, taken to its logical extreme, makes no testable predictions. It simply explains away all evidence that contradicts it. That's not science, it's conspiracy thinking. A more productive approach would be to consider what kinds of evidence might reasonably distinguish between natural and artificial origins, while acknowledging that sufficiently advanced technology could potentially fool any test we might devise. For instance, we might look for patterns in the timing or targeting of interstellar visitors. If probes were being sent to monitor developing civilizations, we might expect them to arrive during periods of rapid technological development or social change. The fact that 3I-ATLAS arrived during humanity's early space age might be coincidence, or it might reflect intelligent timing. We might also look for coordination between multiple interstellar objects. Natural visitors should arrive randomly, with no correlation between their properties or trajectories. Artificial probes might show subtle patterns that reflect common origin or coordinated mission planning. Over longer timescales, we might expect to see changes in the characteristics of interstellar visitors as our own technology advances. Natural objects should show random variation in composition and behavior. Artificial probes might become more sophisticated over time, adapting their camouflage to fool increasingly sensitive instruments. None of these patterns have been observed, but our sample size remains tiny, just 3 confirmed interstellar objects over 8 years. Statistical analysis requires much larger datasets than we currently possess. The probe hypothesis also raises questions about motivation and logistics. Why would an advanced civilization need to send physical probes when they could potentially gather the same information through long-range sensing? Our own technology is approaching the point where we could detect biosignatures in exoplanet atmospheres from dozens of light-years away. A civilization thousands of years more advanced might be able to conduct detailed planetary surveys without leaving their home system. Physical probes would be necessary only if you needed information that couldn't be gathered remotely, or if you wanted to establish a local presence for more direct intervention. The first possibility suggests that whoever built the probes is interested in details we can't imagine. Perhaps quantum-level analysis of our technology, monitoring of individual human behavior, or assessment of cultural and psychological factors that can't be measured from a distance. The second possibility is more ominous, implying that the probe is a precursor to direct contact or intervention. Under this scenario, 3I-ATLAS might be conducting final reconnaissance before its builders make themselves known, or gathering intelligence for purposes we'd prefer not to contemplate. But we're speculating far beyond what the evidence supports. NASA's assessment remains the most reasonable interpretation of current data. 3I-ATLAS appears to be a natural comet with unusual but explicable characteristics. Its high carbon dioxide content reflects formation conditions in its birth system or modifications during its interstellar journey. Its chemical activity follows predictable patterns as solar heating penetrates deeper into the nucleus. The polarization measurements that initially sparked speculation about unusual dust properties remain preliminary and awaiting peer review. Even if confirmed, they would most likely point toward interesting mineralogy rather than artificial materials. Perhaps the most telling argument against the probe hypothesis is the sheer inefficiency of the approach. If an advanced civilization wanted to study our solar system, they could presumably build a much more capable observation platform and place it in a stable orbit around the Sun or one of the outer planets. Using a comet as camouflage makes sense only if stealth is absolutely critical. If revealing their presence would somehow be catastrophic for either their mission or our development. This brings us back to the broader questions raised by the Fermi Paradox. If advanced civilizations exist but remain hidden, what are they afraid of? What are they waiting for? And what would it mean for humanity if we're living under the watchful eyes of cosmic neighbors who prefer to observe from the shadows? These questions become even more profound when we consider what the discovery of artificial probes would mean for our species and our future. Part 13. Implications for humanity. The detection of an artificial probe in our solar system would represent the most significant event in human history, not just scientifically, but philosophically, culturally, and psychologically. It would force us to confront fundamental questions about our place in the universe, our future as a species, and the nature of intelligence itself. Let's start with the immediate implications. Proof that we're being observed by an advanced civilization would instantly resolve the Fermi Paradox, but in perhaps the most unsettling way possible. We wouldn't be alone, but we also wouldn't be in control of our cosmic destiny. The realization that invisible watchers have been studying us, perhaps for centuries or millennia, would fundamentally alter how we think about human autonomy and free will. Every major decision in human history, the development of agriculture, the rise of civilizations, the scientific revolution, the space age, might have been observed and recorded by entities whose capabilities we can barely imagine. Our wars, our art, our technological achievements, our social struggles, all of it might be data points in some vast alien database, entries in a cosmic catalogue of developing civilizations. This knowledge would likely trigger what psychologists call ontological shock, a fundamental crisis about the nature of reality and our place within it. Some individuals and cultures might respond with despair, feeling diminished by the revelation that we're essentially specimens under observation. Others might feel liberated, seeing confirmation that intelligence is common in the universe, and that our problems are part of a larger cosmic story. Religious and philosophical systems would face unprecedented challenges. Many human belief systems place humanity at the center of cosmic significance, whether through divine creation, spiritual evolution, or rational enlightenment. The discovery that we're junior members of a galactic community would require massive theological and philosophical adjustments. But the implications go far beyond immediate psychological impact. The existence of advanced alien observers would raise urgent questions about the rules governing our cosmic neighborhood. Why haven't they made contact? What are they waiting for? What criteria must we meet before open communication becomes possible? If the zoo hypothesis proves correct, we might be living under something like cosmic quarantine, protected but isolated, until we reach sufficient maturity for galactic citizenship. This would suggest that our current historical moment is particularly crucial. The decisions we make about technology, environment, warfare, and social organization might determine whether we graduate to the next level of cosmic civilization or remain indefinitely isolated. The pressure to get it right would be enormous. Every global crisis, climate change, nuclear proliferation, artificial intelligence development, biotechnology risks, would take on cosmic significance. We'd be performing not just for ourselves and future human generations, but for unseen judges whose standards we don't understand. Alternatively, if the dark forest hypothesis were correct, the implications would be even more dire. Discovery of alien probes might mean we've already been targeted for elimination, with the surveillance phase preceding more direct action. Under this scenario, our top priority would be developing defensive capabilities and possibly going into hiding ourselves, ceasing radio transmissions, masking our technological signatures, and preparing for cosmic conflict we're unprepared to fight. The economic and political implications would be staggering either way. Space programs would receive unlimited funding as humanity scrambled to understand our cosmic situation and develop appropriate responses. International cooperation would become essential. The discovery that we're being watched by aliens would make human conflict seem petty by comparison. Scientific research would be revolutionized. Every aspect of physics, biology, and technology would be re-examined in light of the knowledge that far more advanced science exists. We'd be faced with the humbling realization that our proudest achievements, quantum mechanics, relativity, molecular biology, computer science, represent early steps in intellectual journeys that others have completed long ago. But there's another possibility we must consider. What if 3I-ATLAS and other interstellar visitors are entirely natural, but still profound in their implications for understanding cosmic life? Even natural interstellar objects tell us extraordinary things about our galactic neighborhood. They're samples of planetary formation processes from other star systems, carrying information about the chemical and physical conditions that prevail elsewhere in the galaxy. By studying their compositions, structures, and behaviors, we're conducting a form of comparative astronomy that would be impossible any other way. The unusual chemistry of 3I-ATLAS, its high carbon dioxide content, emerging cyanide, and complex organic compounds, provides a window into conditions around distant stars. If life requires specific chemical precursors and environmental conditions, then interstellar visitors help us map the distribution of potentially life-supporting chemistry throughout the galaxy. Each comet, asteroid, or other object from interstellar space represents millions of years of cosmic history compressed into a single messenger. They've traveled between stars, experienced the cold and radiation of deep space, and arrived in our solar system carrying news of worlds we may never visit directly. The growing catalogue of interstellar visitors, Oumuamua with its puzzling properties, Borisov with its familiar chemistry, and now 3I-ATLAS with its distinctive composition, is beginning to sketch the first crude portrait of our galactic neighborhood's diversity. Some stellar systems produce objects that look familiar. Others generate visitors with exotic properties that challenge our understanding of planetary formation. This diversity has profound implications for astrobiology. If the building blocks of life are distributed unevenly throughout the galaxy, then life itself might cluster in certain regions while remaining rare elsewhere. Alternatively, if complex organic chemistry is common, as suggested by the detection of cyanide and other organic compounds in 3I-ATLAS, then the raw materials for life might be available almost everywhere, increasing the odds that biology has emerged independently around many different stars. The upcoming Vera Rubin Observatory will transform interstellar visitor research from a study of rare curiosities into systematic astronomy. With dozens of new objects detected annually, we'll be able to analyze the statistical properties of interstellar populations, their size distributions, chemical compositions, origin directions, and behavioral characteristics. This transformation will provide unprecedented insight into planet formation processes throughout our region of the galaxy. We'll learn whether solar systems like ours are typical or unusual, whether the chemistry that gave rise to Earth's biosphere is common or rare, and whether the materials necessary for technological civilization are widely available or limited to special environments. Perhaps most importantly, systematic study of interstellar visitors will help us understand the processes that might someday spread life and intelligence throughout the galaxy. If natural mechanisms regularly transport complex organic chemistry between star systems, then life might not need to evolve independently everywhere. it might spread through cosmic contamination, seeding new worlds with the chemical precursors necessary for biology. This process, known as panspermia, remains highly speculative, but interstellar visitors provide the most direct way to test its possibility. If we were to discover clearly biological materials in incoming comets, fossilized microorganisms, complex biomolecules, or chemical signatures of metabolic processes, it would revolutionize our understanding of life's distribution throughout the cosmos. Even without finding direct evidence of extraterrestrial life, the chemical diversity revealed by interstellar visitors expands our understanding of what kinds of environments might support biology. Each unusual composition, each exotic chemistry, each unexpected behavior adds to the catalogue of possibilities that astrobiologists must consider when assessing the potential for life elsewhere. From this perspective, 3I-ATLAS is significant whether or not it represents alien intelligence. As a natural object, it's a messenger from distant worlds, carrying samples of chemistry and physics from stellar environments we're only beginning to understand. As a potential artificial probe, it would represent the most important discovery in human history. Either way, its passage through our solar system marks a moment of transition in humanity's cosmic perspective, the beginning of our transformation from a single-planet species wandering about cosmic neighbours into active participants in galactic-scale astronomy and astrobiology. But questions remain about how this transformation will unfold, and whether the universe will continue to reveal its secrets gradually, or surprise us with revelations that change everything overnight. Part 14. The Future of the Paradox. As 3I-ATLAS fades into the cosmic distance, carrying its secrets back toward the space between stars, we're left with more questions than answers. But perhaps that's exactly as it should be. The Fermi Paradox isn't a problem to be solved so much as a framework for understanding our relationship with the larger universe. Our interstellar visitor has taught us that the space between stars isn't empty and sterile, but filled with wandering messengers carrying samples of chemistry from distant worlds. Each visitor adds another piece to the slowly emerging puzzle of galactic diversity, helping us understand the range of conditions that exist in stellar systems throughout our cosmic neighborhood. The unusual composition of 3I-ATLAS, its carbon dioxide dominance, emerging cyanide, and complex organic chemistry, suggests that our local region of the galaxy produces a wider variety of chemical environments than we might have expected. Some stellar systems, like the one that produced 2I divided by Borisov, generate objects chemically similar to our own solar system's comets. Others, like the birthplace of 3I-ATLAS, operate under different conditions that favour carbon dioxide retention over water ice. This chemical diversity has profound implications for understanding the distribution of potentially life-supporting environments throughout the galaxy. If the building blocks of biology, water, carbon compounds, complex organic molecules are unevenly distributed, then life itself might be clustered rather than uniformly spread among the stars. The polarization measurements and other unusual properties detected in 3I-ATLAS, while still awaiting peer review and confirmation, hint at even greater diversity in the physical properties of interstellar materials. Different dust grain sizes, compositions, and structures reflect different formation and processing environments, each telling a story about conditions in distant protoplanetary disks. But the most intriguing aspect of our growing catalogue of interstellar visitors might be what it suggests about the dynamic nature of our galactic environment. We're not isolated in a static cosmic neighbourhood, but embedded in a complex system where materials, and potentially information, flow regularly between stellar systems. This flow of interstellar visitors is about to increase dramatically. The Vera Rubin Observatory, when it begins full operations, is expected to discover dozens of interstellar objects annually, transforming them from rare curiosities into a regular subject of astronomical research. Within a decade, we might have hundreds of examples to study, allowing statistical analysis of their properties and origins. This wealth of data will revolutionize our understanding of the Fermi Paradox itself. Instead of asking, "Where is everybody?" we might find ourselves asking, "What patterns do we see in the cosmic debris field? And what do they tell us about the prevalence and distribution of complex chemistry, planetary systems, and potentially even life throughout the galaxy?" The search for techno-signatures, evidence of alien technology, will also evolve as our sample size grows. With hundreds of interstellar visitors to examine, we'll be able to establish much better baselines for normal behavior making genuinely anomalous objects stand out more clearly against the background of natural variation. If artificial probes are operating in our solar system, disguised among the natural population of interstellar visitors, the statistical approach might eventually reveal them through subtle patterns invisible in small samples. Coordination between objects, systematic changes in properties over time, or responses to human technological development might become apparent only when viewed across large numbers of visitors. But even if all interstellar objects prove to be entirely natural, their study will contribute to solving the Fermi Paradox by helping us understand the prevalence of conditions necessary for life and intelligence throughout the galaxy. Each chemical composition, each unusual property, each unexpected behavior adds to our understanding of cosmic diversity and the range of environments where biology might take hold. The upcoming Nancy Grace Roman Space Telescope will add infrared capabilities that complement ground-based surveys, while the proposed habitable exoplanet observatory will search for biosignatures in the atmospheres of nearby worlds. Together, these instruments will provide an unprecedented view of life's potential distribution throughout our cosmic neighborhood. As our observational capabilities improve, we might discover that the universe isn't silent at all. We've simply been listening in the wrong ways. Advanced civilizations might communicate through gravitational waves, use quantum entanglement for instantaneous information transfer, or employ modulation techniques so sophisticated that their signals appear indistinguishable from cosmic background noise. The development of artificial intelligence on Earth might also change how we approach the search for extraterrestrial intelligence. AI systems, capable of analyzing vast datasets, recognizing subtle patterns, and processing information at superhuman speeds might spot evidence of alien technology that has been hiding in plain sight within our astronomical databases. But perhaps the most profound change in our understanding of the Fermi Paradox will come from recognizing that silence doesn't necessarily imply absence. A universe filled with patient, subtle civilizations operating on timescales of millions of years might appear quiet to species like ourselves, who have been broadcasting for less than a century and listening seriously for only a few decades. From the perspective of galactic history, we're newcomers who just started talking. The fact that we haven't received immediate responses might say more about cosmic courtesy than cosmic emptiness. Advanced civilizations might be waiting for us to demonstrate wisdom, maturity, and responsibility before opening formal diplomatic relations. In this context, our current historical moment becomes particularly significant. We're living through humanity's transition from a single-planet species to a potentially interstellar civilization. The decisions we make about technology, environment, and social organization during this transition might determine whether we eventually join the galactic community or remain indefinitely isolated. The study of interstellar visitors like 3I-ATLAS provides valuable perspective on these choices. Each object carries information about the long-term evolution of stellar systems, the processes that shape planetary environments, and the ultimate fate of worlds like Earth. They're time capsules from the cosmic past and harbingers of potential futures. Whether 3I-ATLAS carries only natural chemistry or something more extraordinary, its passage through our solar system has enriched our understanding of the universe we inhabit. It has shown us that space is not empty, that our cosmic neighborhood is dynamic and diverse, and that the materials necessary for complex chemistry and potentially life are more widely distributed than we might have hoped. Most importantly, it has reminded us that we're part of something larger than ourselves, participants in a cosmic story that began billions of years ago and will continue long after our species has either transcended its current limitations or joined the ranks of cosmic silence. The universe, it seems, is patient. It sends us messengers like 3I-ATLAS, not with urgent communications, but with gentle invitations to look beyond our immediate concerns and consider our place in the grand cosmic conversation. Whether we're wise enough to accept that invitation remains to be seen. Part 15. Closing Meditation. Imagine, for a moment, that you're traveling alongside 3I-ATLAS as it continues its ancient journey through our solar system. You're moving at 19 kilometers per second, fast enough to circle the Earth in less than an hour, yet barely crawling by the standards of interstellar space. Around you, the darkness is punctuated by the distant glow of our sun, growing brighter with each passing day as you approach your closest encounter with our star. Behind you stretches a path through the galaxy, that began millions of years ago in a stellar nursery so distant that its light has barely reached Earth. You've drifted through the cosmic void, past failed stars and dying suns, through clouds of gas and dust where new worlds are being born, carrying with you the chemical signature of your birthplace like a cosmic fingerprint. You are older than complex life on Earth, older than the oxygen in our atmosphere, older than the continents beneath our feet. You have witnessed the rise and fall of countless stellar generations, the birth and death of planetary systems, the slow waltz of galaxies through the expanding universe. You are, in the most literal sense, a traveller from deep time, as well as deep space. Now, as you warm in the light of an alien sun, you begin to awaken. Ancient ices sublimate into gas, carrying with them complex molecules that have been frozen since the early days of the galaxy. Carbon dioxide streams away from your nucleus, along with carbon monoxide, water vapor, and the cyanide compounds that give you a faint green glow in the cosmic darkness. To the inhabitants of the third planet from this yellow star, you represent mystery. They point their instruments at you, analyze your light, and debate your nature in their academic journals and conference halls. Some see you as a natural wonder, a sample of pristine materials from the galactic deep. Others wonder if you might be something more, a messenger, a probe, a sign that they are not alone in their cosmic neighborhood. They don't yet know that the answer might be both, or neither, or something entirely beyond their current understanding. The universe operates on scales of space and time that dwarf individual civilizations, individual species, individual worlds. What appears mysterious to them might be commonplace on galactic scales. What seems impossible to their science might be elementary physics to civilizations a million years older. But perhaps the most beautiful thing about your visit is not what you are, but what you represent, the universe talking to itself. You are a conversation between stellar systems, a chemical dialogue carried out across impossible distances and unimaginable time spans. The carbon in your nucleus was forged in the heart of a dying star. The water ice that once coated your surface formed in the cold outer regions of a protoplanetary disk. The complex organic molecules streaming from your coma tell stories of chemistry that unfolded over cosmic eons. In studying you, the inhabitants of this small blue world are learning to read the universe's own language, the vocabulary of atoms and molecules, the grammar of physics and chemistry, the poetry of cosmic evolution. They are discovering that they too are part of this conversation, built from the same stellar ash, shaped by the same physical forces, participating in the same grand narrative that connects all matter and energy across space and time. Maybe the universe isn't silent after all. Maybe it speaks constantly, through wanderers like you, through the light of distant stars, through the patient accumulation of knowledge that turns mystery into understanding. Maybe intelligence isn't rare, it's inevitable, emerging wherever matter and energy and time combine in sufficient complexity and duration. Maybe the inhabitants of this world aren't looking for cosmic neighbors because they're alone, but because they're finally ready to recognize that they were never alone at all. They're part of a universe that thinks, that creates, that dreams across scales and durations that make their brief individual lives seem like single thoughts in a vast cosmic mind. As you continue your journey past their sun and back toward the space between stars, you carry with you not just the ancient chemistry of your birth, but also something new, the knowledge that at least one world in this stellar system has produced beings capable of wonder, beings who look up at the night sky and ask the deepest questions about existence, meaning, and their place in the cosmic story. Whether they ever receive direct answers to those questions is less important than the fact that they're asking them. In a universe where most matter remains forever unconscious, where most worlds never develop life capable of contemplating its own existence, the emergence of questioning intelligence is itself a kind of answer, a proof that the cosmos is not merely a collection of particles obeying physical laws, but a system capable of understanding itself through the thoughts and observations of its conscious components. You are part of that system, as are the beings who watch your passage with their telescopes and their theories, and their sense of wonder. You are all temporary arrangements of ancient atoms, brief patterns in the flow of cosmic evolution, momentary expressions of the universe's endless creativity and complexity. And in this moment, as your path carries you past their world and toward distant encounters with other suns, other planets, other possibilities for connection and understanding, you embody the most profound truth of cosmic existence. Everything is connected, everything is temporary, and everything is participating in a conversation too vast and patient and beautiful for any single participant to fully comprehend. The silence of the stars, it turns out, was never really silence at all. It was just the universe, waiting for its children to learn how to listen. Sleep well, knowing that you are part of this cosmic conversation, this grand dialogue between matter and energy, between order and chaos, between the known and the unknowable. Tomorrow, you will wake to a universe that continues to reveal its secrets. One wandering visitor, one distant signal, one moment of wonder at a time. The mystery remains, but so does the promise. We are not alone, we have never been alone, and the conversation is just beginning.